Hello friends, welcome to the course Essentials of Data Science with R Software 1, in which we are trying to understand the basic concept of probability theory and statistical inference. So, you can recall that in the last lecture we had understood the concept of unbiased estimators, and towards the end of the lecture I had shown you that there are 4 possible estimators which are trying to estimate the population mean of a normal population, and all those 4 estimators were unbiased estimator for the population mean mu. So, the question was, out of them which one we have to choose, and in order to find the answer of such a question we need to have some more criteria, right. That is the same thing that suppose in a class there are 2 students who have got this 100% marks, and then we have to decide that who is going to be at the first position and who is going to be at the second position. So, sometime we make a rule that okay, if 2 persons have got the same marks, then we will try to compare the marks in their particular subject, for example say mathematics, and even if the mathematics marks are same, then we go for physics or chemistry and so on. So, we try to impose some conditions, right. That is the same thing that in a soccer game also, in the football game also, if both the teams are striking the same number of goals at the end of the game, we try to give them the penalty strokes, and the team which strokes more goal, that team is said to be the winner. Similarly, here in statistical inference also we need to impose some more criteria gradually, so that we get a good estimator. But now in this lecture we are going to talk about the efficiency of the estimator. That means we are going to impose one more criteria of efficiency on these estimators, and we will try to choose the estimator which is more efficient. But now the bigger question comes, how are you going to define the efficiency? Tell me one thing, suppose in an office there are 2 workers who are trying to do the same job, say typing. How do you say that which of the 2 typists is a better typist? You simply try to say the typist which is making the smaller number of typing mistakes, that person is said to be better than the other typist. And similarly, in general we always say that a person is efficient, that if the person can do the job in the less time with less number of mistakes. So, similar concept is there in statistics also, but the question is now how to measure this efficiency. So, we know the concept of variability. We always want a statistical decision in which the variability should be as small as possible. For example, as earlier I had discussed an example where you have to find out the time taken from your home to your college. Now, you have 2 options, you get me the value say 20 minutes, and you say the variability will be just by 1 to 2 minutes. That means you can take the time between 18 minutes to 22 minutes, right. But if you say okay, the average value is 20 minutes, but the variability will be say between say 15 to 20 minutes, that means what? You are trying to say, well, the average value is 20, but the actual value will be something like 15 to 20 minutes less than the 20 minutes and 15 to 20 minutes more than the 20 minutes. Or similarly, if you try to say that your friend is coming at a particular point, so sometimes you say that okay, the friend will be getting late by 5 minutes. So, that means if the waiting time is going to be just say not more than 5 minutes, but if the person says okay, he may get or delayed say between say this 30 minutes to say 40 minutes, right, then that means the whatever the time the person has given to reach, that can be less than 30 minutes from that time or after the 30 minutes of that time. What do you think, which of the statement is better? So, definitely where you are getting less variability, the person says that okay, I will be there within plus minus 5 minutes or within plus minus 20 minutes. The statement within plus minus 5 minutes is said to be a more efficient estimator or a more efficient value. So, similarly, in the case of statistical estimation, we try to compute the variance of these statistics, and these statistics are the random, and since these estimators are going to be the functions of the random variable. So, that is why they are statistics, and so we can find out their variance also. So, now that is the topic which we are going to discuss in this lecture, and once we try to impose the criteria of this smaller variability, after that some more topics will come that I will try to discuss in this lecture. So, let us begin our lecture. Okay, so now we talk about efficiency of estimators. So, now you can recall our discussion when we discussed the development of the concept of variability. We had estimated a parameter theta by theta hat. Now, there are two options. I tried to measure the deviation of theta hat from theta like this, theta hat minus theta, or if I try to measure the deviation of theta hat from theta in terms of its mean value. So, I try to consider here theta hat minus expected value of theta hat. So, now using these two concepts, we have two measures of variability. One is here variance and another here is mean squared error. So, we define the variance of an estimator theta hat as variance of theta hat equal to expected value of theta hat minus expected value of theta hat whole square, and the mean squared error of an estimator theta hat is defined as expected value of theta hat minus theta whole square. So, now means taking expectation with respect to the mean value expected value of theta hat or theta, that is not a very difficult job for you, that you can do very easily, but this is how we define the two concepts of variability when we are talking of the efficiency of the estimator, that the estimator has been obtained as theta hat. Now, we want to measure its variability. So, remember one thing, that you can estimate the variance of theta hat, or you can also estimate MSE of theta hat depending on the situation what we really want to do, but these are the two measures about which we are going to talk about. So, definitely when you are talking of the mean squared error, or that is commonly called as MSE. So, this M is for mean, S is for squared, and is for error. So, this MSE of theta hat is defined like this, expected value of theta hat minus theta whole square, and if you try to just add and subtract here the expected value of theta hat inside the bracket, and if you try to expand it, you can write down here very clearly as the variance of theta hat plus expected value of theta hat minus theta whole square, and if you try to identify what is this thing, this is nothing but your bias of theta hat. So, the MSE of theta hat can be expressed as the sum of variance of theta hat plus square of the bias of theta hat. So, this MSE combines bias and variance into one measure, right. And you know that this bias and variance both are the properties of an estimator that are trying to characterize the estimator, right. And now, we are looking for those estimators, or we are going to call any estimator as a good estimator whose bias should be as small as possible and the variability or the variance should be as small as possible, right. So, we search for say quote unquote good estimators in the sense that bias and the variance are as small as possible, and once you do it, and the accuracy of the estimator becomes as high as possible. But when we try to do such exercise mathematically, then it turns out that we cannot minimize both the measures simultaneously, that is the bias as well as variance, both of them cannot be minimized at the same time. And so, there is always a bias variance trade off, that means you have to strike a balance between the amount of bias in the estimator and the variance of the estimator, right. Now, the question comes that how are you going to define that which of the estimator is going to be more efficient, right. So, suppose there are two parameters, right, for a parameter theta, and this theta has the parametric space which is here capital theta, like this one, right. So, theta belongs to capital theta. So, yeah, be careful about my wordings. When I say theta, theta means small theta, and when I have to speak out for this capital theta, then I will always say capital theta. Right. Okay. So, now suppose we want to estimate this parameter theta, and suppose theta 1 hat and theta 2 hat are the two estimators of theta, and suppose both are unbiased, right. So, then in this case theta 1 hat is said to be more efficient than theta 2 under the criteria of variance for estimating the parameter theta when variance of theta 1 hat is less than or equal to variance of theta 2 hat for all theta belonging to capital theta, and variance of theta 1 hat is strictly less than variance of theta 2 hat for at least one theta belonging to capital theta. Right. So, in general you are trying to say that any estimator whose variance is going to be less, that will be called as more efficient than the other estimator whose variance is higher than this, right. Now, the same definition can also be given in terms of the mean squared error of theta 1 hat and theta 2 hat. But in this case we assume that let theta 1 hat and theta 2 hat be the biased estimators of theta, right. So, now in this case theta 1 hat is said to be more efficient than theta 2 hat under the criteria of mean squared error, or we call it say MSE criteria for estimating the parameter theta when MSE of theta 1 hat is less than or equal to MSE of theta 2 hat for all theta belonging to capital theta, and MSE of theta 1 hat is strictly less than MSE of theta 2 hat for at least one theta belonging to theta, right. So, that is what we try to do, and another way to measure the efficiency of estimator is the relative efficiency. That means, you try to compare the variances or MSEs of theta 1 hat and theta 2. So, the relative efficiency of theta 2 hat to theta 1 hat is defined as variance of theta 1 hat divided by variance of theta 2 hat. Right, and obviously, if this relative efficiency is less than 1, that means I am trying to say here variance of theta 1 hat is less than variance of theta 2 hat. That means, if this ratio is less than 1, that means it is implying that variance of theta 1 hat is less than variance of theta 2 hat. So, obviously, this theta 1 hat becomes more efficient. So, now we can say that if this relative efficiency is less than 1, you would conclude that theta 1 hat is a more efficient estimator than theta 2 hat, in the sense that it has a smaller variance. And similarly, if you want to define the relative efficiency in terms of MSE, then the relative efficiency of theta 2 hat to theta 1 hat is defined as exactly in the same way. You simply have to replace variance by MSE. So, that will become MSE of theta 1 hat divided by MSE of theta 2 hat, and if this relative efficiency is less than 1, you would conclude that theta 1 hat is a more efficient estimator than theta 2 hat, in the sense that it has a smaller mean squared error, right. So, now in case if you try to see graphically what will really happen, right, that suppose we have got suppose two estimators theta 1 hat and theta 2 hat. So, now both the theta 1 hat and theta 2 hat, suppose they are unbiased estimator, obviously they are random variable, because they are the function of random variable. So, they are statistic. So, now once they have got a random variable, then these statistics will also have a probability distribution. And you have done such a thing. For example, when you said that let x1, x2, xn, they are coming from normal mu sigma square, and suppose they all are IID, identically and independently distributed, then the distribution of the sample mean is also normal with mean mu and variance sigma square upon n. So, similarly, you can think in general that that all the estimators will also have a sampling distribution, right. So, suppose I try to plot sampling distribution of the two statistics theta 1 hat and theta 2 hat, which are being used to estimate the same parameter theta. Suppose their curves looks like this. So, you can see here that in the case of theta 1 hat, this variability which is indicated by the curve, that is much smaller than the variability which is exhibited by the sampling distribution of theta 2 hat. So, this is how you can see that this criteria can be looked upon, right. In fact, when we are trying to talk about this variance and MSE, then you have seen that there is a specific condition that variance is defined when the estimator is unbiased, and MSE is usually defined when the estimator is biased. And obviously, if you try to look into the expression of this MSE here, you can see very clearly here that in case if this bias becomes here 0, if this is equal to 0, then variance is equal to MSE. Then means MSE and variance both become the same, right. So, that is why we have these two definitions, but what I want to tell you here that in practice many times we are dealing with some situations where the biased estimators are preferable to unbiased estimators, because they have a smaller mean squared error. And suppose we want to have an estimator which has got a lower variability, and the criteria of biasness is not that important in a given situation. So, in those situations this type of concept is useful, and we may be able to reduce the variance of the estimator considerably just by introducing a relatively small amount of bias, right. And as long as the reduction in the variance is greater than the squared bias, an improved estimator from a mean square error point of view will result, right. For example, you might have heard the name shrinkage estimation. The shrinkage estimation is an example of this type of estimation, that we try to strike a balance between the bias and the variability, and we get an estimator which is biased, but that has a smaller variability than the variability of an unbiased estimator. But anyway, we are not going to talk about this concept here, but surely I would like you to know that that there exists such estimator. Okay. And in case if we are considering only the unbiased estimator of theta, suppose there is a parameter theta, and there are suppose more than one estimators which can estimate it like this one. Then what we will try to do, that we will try to find out here the variance of each of this estimator, variance of theta 1 hat, variance of theta 2 hat, and so on. And then I will try to see that which of this variance value is the minimum. So, what is happening? Now, we have here all the estimators which are unbiased, and now out of them we are trying to choose the estimator out of this for which the variability is the lowest, the minimum. This type of estimator, don't you think, can be called as minimum variance unbiased estimator, right. So, this is also an outcome, that once you are trying to find out the estimator, you have to impose a condition that any estimator whose variance will be less, that will be more preferable, right. So, if we consider all unbiased estimators of theta, the one with the smallest variance is called the minimum variance unbiased estimator, and that is briefly denoted as MVUE. M means minimum, V means variance, U means unbiased, and E means estimator, right. So, in a sense the MVUE is the most likely among all unbiased estimator to produce an estimate that is close to the true value of theta. So, now what you have done, suppose if I try to explain you here, then suppose we have an unknown parameter theta, and then we had here, suppose here k possible estimate, theta 1 hat, theta 2 hat, up to here say theta k hat. Now, I try to divide them into two groups. One are here unbiased estimators, and then another is a group of biased estimators, right. So, definitely there will be suppose more than two estimators in both the cases, right. So, there will be theta 1 hat, theta 2 hat, and something like this, and here also some theta hats are there. Now, what we try to do, that we ignore the all theta hats which are biased, and we then we try to find out the variances of all theta hats which are unbiased, and then out of them I try to choose the estimator which has got the smallest variance, and this is called as MVUE, and that is the way we are trying to say that when the variance is low. So, we expect that the estimated value is going to be more closer to the true value, right. So, whenever in practice we are working and whenever we are trying to estimate a parameter, we always have to report the estimate of this variance, that what is the variability which is expected from that given estimator. So, you know that variance is a squared quantity, and for example, if I have a random variable here height, then suppose height is measured in meters. So, variance will be measured in meter square. So, in practice it becomes many times convenient that instead of reporting the values in terms of squared quantities, we want to report them in the same quantities. So, one option is that if you want to convert this meter square into the same unit meter, one can take the square root. And when we try to find out the estimate of the variance, that means we are trying to find out the value of the variance of the estimator on the basis of given sample of data, and then we try to take its positive square root, that is called as standard error, right. So, when the numerical values of point estimate of a parameter is reported, it is usually desirable to give some idea about the precision of the estimation or the variability of the estimator. So, the measure of precision usually employed is the standard error of the estimator that has been used, right. And then remember one thing, we are using here the term standard error, we are not using the term here standard deviation, that we already have discussed in one of the earlier lecture, that what is the difference between standard deviation and standard error. The standard deviation is for the population value, and this quantity and this expression will involve some population parameter, but the standard error is entirely based on the sample values, right. So, if I am trying to estimate a parameter theta by theta hat, then the standard error of theta hat is the positive square root of its estimated variance, which is given by like this, square root of estimator of variance of theta and its positive square root. And you see, you are trying to find out here the value of variance of theta hat, and you are trying to estimate it. So, we know that when we are trying to estimate it, I have to put here a hat. So, that is why I am trying to put here a big hat, so that you can know that this entire quantity is estimated, and then I am trying to take its square root, that will have two possibilities, plus sign and minus sign. So, I am trying to take here the positive sign, right. So, this is a very nice expected desirable value that any experimenter would like to have in real life, but surely finding an estimator of the variance is always not so simple and straightforward, because that may involve some unknown parameter value also, because whenever you are trying to find out the variance of theta hat, that is going to be a complicated function, and that may involve some parameters which are unknown. So, you just cannot estimate it, but in real life whenever we are trying to work, we always want to have it, because that is the same situation that somebody goes to a doctor, and if the doctor says no, we do not have the medicine for this disease, then it is not a very nice thing to say, and nobody will be happy. But if the doctor says that okay, we do not know about the right medicine for this disease, but there are some possible medicines and we are trying to use them, right. So, it is possible that if the ailment can be cured in say 5 days of time, in case if the medicine would had been developed, but now the ailment is going to be say cured in say 3 more days. So, instead of 5 days, it is assured that it will get cured in 8 days. So, now if I ask you what is a better option, that the doctor do not gives a medicine, that there is no medicine for this ailment, or the doctor tries to give you some good medicine, or the doctor tries to give the patient some good medicine that is expected to cure it say in say couple of days more. So, that is not going to be as efficient as the true medicine, but definitely that is not going to be a bad solution also. So, ideally one always needs to find the estimate of the variance, but if the variance involves a known parameter, then a simple solution that is employed in real life is to replace the unknown parameter by their estimators and obtain the standard error. So, this is something like a feasible version, right. So, you may not get here the exact value, but you will get a nice or good approximate value, right. So, now let me try to take a simple example to explain you this feature, that suppose we have a random sample x1, x2, xn of size n from normal mu sigma square, then we know that the sample mean of x1, x2, xn will follow a normal distribution with mean mu and variance sigma square upon n, that we already have done, right. Now, the standard deviation of x bar is defined here as say square root of sigma square upon n. So, now you can see here there is a quantity which is here sigma square involved. So, now this standard deviation is going to be known only when sigma square is known to us, and in practice usually this will not be known to us, because we will be working only on the basis of a random sample. So, one option is this that when sigma square is unknown, then it can be estimated by, for example, this quantity s square is equal to 1 upon n minus 1 summation I go from 1 to n x I minus x bar whole square. Yes. The question is how this quantity is coming, that we will try to see when we are trying to find out the estimator of say mean and variance in the case of normal population in the forthcoming lectures. But at this moment you can just take it as this is one possible choice for estimating the value of sigma square. So, this is actually like sigma square hat, right. So, now what we can do, we can replace this sigma square by this quantity sigma square by here sigma square hat, and then we have this quantity here square root of s square upon n. This is the standard deviation which is obtained after replacing the unknown sigma square by sigma square hat, and this is called as standard error of x bar, right. But now the problem is that the statistical properties of variance of x bar, it is standard deviation, estimate of variance of x bar and standard error, they are different. They have got different statistical properties, and having one property does not directly employ the properties of the other estimators. So, that is what you have to keep in mind, but still we are looking forward for a solution. So, definitely the first choice will be if you can find out the exact value of an estimator of the variance or MSE, and if not, one possible solution which can be easily employed particularly in data sciences is that you try to estimate all the parameters separately, and then you try to replace the estimated value in the place of unknown parameters in the expression of the variance. Possibly this will give you a good value, right. Now, let me try to take here one simple example to explain you these concepts. Suppose we have got a random sample from the normal distribution whose mean is mu and the variance is suppose known as 1, right. So, now we know that expected value of x here is mu, and we already have discussed in the earlier lecture that if I try to consider here 4 possible estimator delta 1 x, delta 2 x, delta 3 x and here delta 4 x, then what is going to happen? We had obtained the bias of all the 4 estimator, and we had shown in the earlier lecture that all these estimators are going to be unbiased estimators of the population mean. So, I am not repeating that algebra. And so, now we have here 4 estimators of the population mean, and we want to know which one is the best estimator. So, we try to now impose here a criteria of variance, and we try to compute the variance of all these estimators, right. So, we are going to find out the variance of an estimator say delta x as expected value of delta x minus mu whole square, and out of them we are going to choose that delta x for which the variance is minimum, and that is going to be called as best unbiased estimator, or that will have uniformly minimum variance unbiased estimator, which is briefly called as UMVUE. U, M, V, U and E, they are coming from here. It is not always that UMV always exist. So, now let us try to see what are we going to do here. One thing you may notice here that sometime I am trying to indicate the estimator of an unknown parameter by theta hat or sometime by delta x. So, means I am just using it conveniently so that I can explain you in a better way. For example, when I am using delta x, that is clearly indicating that this is a function of x, right. So, do not get confused. So, an estimator delta star x is the uniformly minimum variance unbiased estimator of some function of parameter if and only if this estimator, say delta star x, is an unbiased estimator of g theta, that is the spectral value of delta star x is equal to g theta, and variance of this delta star x is always less than or equal to variance of delta x, where delta x is any other estimator of g theta, and delta x is also an unbiased estimator of theta. So, what are we trying to do here? That we are trying to simply choose the estimator from a group or a class of estimators in which all the estimators are unbiased estimators of the given parameter, and then we are trying to find out their variances, and we are trying to find out that whose value is the least, that is which estimator has got the minimum variance, and then we are trying to choose that estimator which has got the minimum variance, and that is going to be called as uniformly minimum variance unbiased estimator of that respective parameter. So, this is the definition of UMVUE of g theta, right. So, obviously, you are now imposing the word here uniformly minimum. So, that means if there are two estimators which have got the same variance, that means there cannot be unique uniformly minimum variance unbiased estimator, right. So, now in the same example which I have just considered, where we had the 4 parameters, just for the sake of understanding I am trying to take here the 3 estimators, and now I am trying to denote them here as say. So, now let me try to take here the example which I just considered, and I try to consider here 3 possible estimators of the parameter mu. So, we have a sample from the normal mu 1, and we want to estimate the parameter mu, and for that we are estimating mu by say mu 1 hat, which is the sample mean, mu 2 hat, which is the mean of the first 2 observation, and mu 3 hat, which is the first observation, right. I am not considering here the delta 4 x, because means otherwise you will get confused, because the condition will be on summation ai square also, right. So, now you can see here we already have found that all the 3 estimators, they are unbiased estimator. Now, we try to find out their variances. So, the variance of mu 1 hat will come out to be 1 upon n, because this is sigma square upon n, and sigma square here is 1. Similarly, if you try to find out the variance of mu 2 hat, this will come out to be here variance of x 1 plus variance of here x 2 plus covariance will become 0, because they are independent, and divided by here 2 square. So, the variance of x 1 and variance of x 2, they are 1 1. So, this will become here 1 plus 1 divided by 4, which is equal to 1 by 2. And similarly, if you try to find out the variance of mu 3 hat, this will be simply here sigma square, which is equal to here 1. So, now you can see here that out of these 3 values, 1 upon n, 1 upon 2, and here 1, this 1 upon n is going to be smaller than 1 upon 2 and 1 if n is greater than 2. Right, and definitely when you are trying to deal with statistics and data sciences, you expect that the observations will be at least more than 2. So, this condition is usually going to be satisfied in all the practical applications, and you can see here that for n greater than 2, the variance of mu 1 hat is minimum among the variances of mu 1 hat, mu 2 hat, and mu 3 hat. So, I can say here that this is the best estimator, right. So, now I try to simulate the same experiment in the R software, just to convince you that how it will look like. So, I try to consider here only 2 estimators just for the sake of simplicity, and this is here mu 1 hat is equal to x bar, and I am considering mu 2 hat equal to x 1. So, both of them are going to be unbiased estimator, and I try to generate the random samples x 1, x 2, x n from normal mu 1, and I try to generate a large number of samples, and I try to see what happens, right. So, this is the program which you can actually use. So, you can see here it is trying to generate the random numbers from the normal population, and then we are trying to find out its say here mean, right. And then we are trying to find out the from the values of mu1 hat and mu2 hat, we are trying to find out their variances, which are you can see here like this one. Okay, so now this is the program here, the screenshot. Now means I already have obtained these values and I would like to discuss it with you. So, you can see here in this case the true value of mu is 10 and the true value of sigma square is 25, by which I have generated these observations. Now, if you try to obtain the value of sigma 1 square hat and sigma 2 square hat, you can see here when you are trying to just take a sample of size 10 and you are getting only 5 samples here, then the value of sigma 1 square hat is coming to be close to 0.51, but can it become 2.35, then it becomes 2.15. So, there is a lot of fluctuation even when you are trying to increase the sample numbers. That means, you are trying to generate 50 sample or say even 5,000 samples, right. And in case if you try to look into the sigma 2 square hat, this value is like 242, 21, 26. So, you can see both the values are fluctuating, they are varying, but definitely the variations in the values of sigma 2 square hat are much larger than the values of variance in the case of sigma 1 square hat. And the same thing you can see here that if I try to increase here the number of observations here to 100 and can I try to generate 50 samples, 500 samples and 5,000 samples here, the values of sigma 1 square hat are close to 0.24, 0.23, 0.25. right, because they are going to be determined by sigma square upon here n, right. So, these values are much closer than the values of sigma 2 square hat. You can see they are close to 18, 25 and 25. So, you can see here that all these variances are greater than the variances that you have obtained using the expression of sigma 1 square hat. So, this clearly shows you that the variance sigma 1 square hat is smaller than the values of sigma 2 square hat in general, and you try to repeat this experiment for a variety of condition whatever you can expect that can happen in the data science, and then try to see possibly you will get an idea that how this variance is are larger or say smaller, and this is the screenshot of the same outcome which I just shown you. Now, let me try to show you this thing on the R console, and then we are done with this lecture also, right. So, I try to copy this program on the R console, you can see here, and then I try to execute it. You can see here this is like here this one. You can see here these are the values like this one, and if you try to increase the number of observations over here, you can see here 100 observations, these values are like this. So, I would like that you try to conduct this experiment and that can you try to convince yourself that and try to understand what is happening inside this phenomena. So, now let me come to an end to this lecture, and I have tried my best to give you the concept of efficiency, and I also have introduced that how this efficiency can be embedded into the estimators, and for that we have defined the minimum variance and bias estimator or say uniformly minimum variance and bias estimator. Yes, the question still remains that how are you going to find out such estimator. So, that we will try to discuss in the forthcoming lectures. So, now you try to have a look, try to experiment these things on the R console, try to take an example from the book, try to solve it manually, means using the statistical concept, and try to simulate it inside the R software. I promise you this will give you a wonderful experience and better knowledge than anybody can have it. So, you try to practice it, and I will see you in the next lecture. Till then, goodbye.